My name is Lee Jongzi and I'm going to present on the process control system.
My name is Nurhayati and I will be presenting on the challenges in process control.
Hi, my name is Suta Ramindran and I'll be presenting recommendation.
My name is Umar bin Abdul Aziz and I'll be presenting on the problem statement, the objectives and the conclusion.
Assalamualaikum. Hi, my name is Fatin Nurdini and I'll be presenting the introduction part for this project. Textile is a flexible material created by multiple processes, creating fabric, clothes, and material. While textile industry concerns regarding the outcome of the product, such as the design, production, and distribution. So with the current economy, fast fashion has always been a go-to place for the shoppers. Due to the processes that the clean water goes through from the inflow, the affluent water leaving the factory is actually highly contaminated if left untreated, especially with strong heavy dyes. So the presence itself actually degrades the water quality by a large margin. Therefore, in this research, we will find multiple ways, challenges, and recommendations for the wastewater treatment station can work with full efficiency.
For the problem statement, the society is well informed that environmental pollution levels are rising with every year that passes by, though many does not know that the industries made their clothing contributes to a large sum of the pollution. The textile industry, where they ironically bring colors into people's life through clothing, leads to a serious pollution of surface water, groundwater and soil, mostly due to the industry not taking care of their textile effluently efficiently. The objective of this project is to study the appropriate control system for a zero waste management textile industry, to determine the characteristics of the process control parameters, to study the effect of flow rate controller in the control system strategy for textile wastewater treatment, and to identify the challenges and solutions to the process control.
The electrocoagulation unit's control setup is shown in Figure 1. A stack of electroplates was connected to a current source as the main component. The data from the turbidity, current, and flow rate sensor is collected by a microcontroller, which then sends it to another microprocessor, which controls the current regulator and base pump. The electrolysis procedure was carried out by passing a direct electric current through the wastewater from the anode plate to the cathode plate. The current caused the surface charge of suspended particles in water to decrease, allowing them to coagulate. The combination overflowed into the transition unit, where the coagulates easily separated from the water due to the fixed volume of the unit. The end outcome was water that appeared to be clearer and had lower turbidity measurements. The sensor were used to measure the process output turbidity as well as the input waste flow rates, which were then gathered in real time by the microcontrollers. The control strategy intended to manipulate the wastewater flow rate to produce the desired turbidity. The difference between the target and the measured turbidity was read by the controller. The controller calculated the control action and sent a PW signal to the driver circuit, which turned on the pump. The turbidity was caused by a change in wastewater flow rate, which changed its residence time in the unit. The change was recognized by the turbidity sensor, which delivered a feedback signal to the controller. The electric current in this controller was assumed to be constant. Proportional and integral PI control was used in control techniques. The use of derivative controllers is avoided since it will reverse P and I efforts and lead the system to achieve the set point at a slower rate than before, and the process dynamics are already slow. The main control objective is to maintain the wastewater flow rate at desired low volume. In a nutshell, the inlet flow of effluent to the electrocoagulation will be set at the highest output-input ratio, which is the maximum flow rate capacity in the initial time to shorten the duration of transit process. When the turbidity sensor senses that there is an occurrence of offset, for example, the output value of turbidity value is higher than the desired value, then the PI controller will send an electric signal to the flow rate controller, and the flow rate controller will changes the flow rate of the input effluent based on the PI controller. Hence, the value of process variable can reach the set point, which eliminates the offset, and there will be no overshoot. This will result the value of turbidity always reach the standard of safe disposal and minimize the pollution of dyes color to the river environment.
Moving on to the challenges concerning the process control in textile industry. The first challenge is scaling of the process from pilot scale study to industrial scale. In pilot scale, researchers simplified it by assuming the effluent had been equalized and neutralized before the process began. First, liquid buffer with the specified parameters was used for stimulating. In real textile effluent, the value of disturbance might exist in the readings and is not guaranteed for consistency, hence risking the control system efficiency. The second challenge is high electricity consumption directly affecting operation costs. Typically, the process utilizes direct current power supply as this supplies the system with both positive and negative charge from the connecting wires. However, this encourages the formation of an oxide layer on the cathode, also known as cathode passivation. This results in a restraint on the flow of current between the electrodes, which then increases the power consumption. Last challenge is sludge produced from electrocoagulation process contains reactive component. As textile wastewater is known to be high in turbidity, salt content, chemical oxygen demand, and total organic carbon, the disposal is still one of the tough and risky jobs. Though it is found that the process itself produces 60% less volume of sludge compared to chemical coagulation, the dissociation of metal ions from the electrode may affect the color of produced sludge.
Recommendation. For the first challenge, which is scaling up the process from pilot scale study to industrial scale, there are two recommendations suggested. Firstly is to use a hybrid electrocoagulation electrodialysis process, and the second recommendation is to use a combination chemical coagulation, electrocoagulation, and adsorption for treating real textile wastewater. For the second challenge, which is the high electricity consumption, which affects the operational cost, this issue can be solved by using an alternative current instead of a direct current. The last challenge, which is the disposal of sludge produced from electrocoagulation process, which contains reactive component, can be solved by stabilizing and solidifying the electrocoagulation sludge and disposing it in a secure landfill, or to reuse it back as construction material for ground improvement purposes.
To conclude, the textile industry contributes largely into the pollution level based on the wastewater discharge. One of the ways to effectively treat the wastewater discharge is through electrocoagulation. We displayed the possible solution for an efficient wastewater discharge through our method and discussion. The recommendations have also solved the challenges that occur in the process control of the system. Thank you.